Hello everyone and welcome to this video on DC steady state in inductors and capacitors. So we are going to analyze RC and RL circuits when it is connected to some source for a very long time. So after a long period of time, the natural exponential response of the RC and the RL circuit is going to vanish. What do I mean? So we know that for an RC circuit, V of t is equal to V naught 1 minus e power minus t by tau. And for an RL circuit, I of t is equal to I naught 1 minus e power minus t by tau. For an RC circuit, let me say the tau c so that I can differentiate it for the two cases. Tau c, the time constant, is going to be RC, whereas for the RL circuit, tau L is going to be L by R. So this is what we know from the previous videos. So here they are saying that when t tends to infinity, this exponential component vanishes and the system attains a steady state where the response is just the DC component. So that is why at t is infinity, the circuit reaches a forced DC response. That is V naught in case of the RC circuit and I naught in case of the RL circuit. Now, if you would remember, V naught is nothing but the source voltage or the voltage of the source to which the RC is connected, and I naught is the current due to the source that R and L is connected to. So now if we look at this response, that is also showing us very clearly that when t tends to infinity, this curve is going to attain V naught for the RC circuit, and at t tends to infinity, this curve is going to attain V naught by R, which is nothing but I naught at t is equal to infinity. Now, having said this, what would be the behavior of the capacitor during the steady state? So, here, from the circuit point of view, what happens is the voltage across the capacitor at t tends to infinity becomes equal to V naught. So, essentially, for this circuit, the voltage at this point and this point become equal. So, there's no potential difference. So, the current is going to become equal to 0. So, there's going to be no current flowing through this branch, which means the capacitor acts like an open circuit. On the other hand, if we look at the RL circuit, for the RL, the voltage across the inductor tends to become 0 as t tends to infinity, because this current I of t is just the DC component, that is the forced response, which is V naught by R. So, therefore, the inductor acts simply like a short circuit in case of the steady state. So, keeping in mind that the capacitor acts like an open circuit and the inductor acts like a short circuit as t tends to infinity, let us look into some numericals related to it. So, this is the first problem. This question was asked in GATE in the doubly paper in the year 22. So, here, when the switch S is closed, the time t is equal to 0. And we need to compute the voltage across this 6 ohms resistor. Now, if we observe this circuit, we can see that the 6 ohms and the 3 ohms are in parallel with each other, and this entire branch is in parallel with the other two branches, the branch with the capacitor and the resistor, as well as the branch with the voltage source and the resistor. So, having said that, let's simplify this circuit. So, we can redraw this as 6 and 3 being parallel to each other. We can replace it with a 2 ohms, because 6 into 3 by 6 plus 3, which is 18 by 9, which is 2 ohms. So we can replace this parallel combination with a 2 ohms resistor. Now this is in parallel with the capacitor and the 10 ohms, and this is in parallel with the 10 volts and a 2 ohms where the switch is closed. We have been asked to compute the steady state voltage. So if we have to compute the steady state voltage with a circuit having a capacitor, then we need to consider that this capacitor is going to act like an open circuit as t tends to infinity. That's when it's going to attain the steady state, right? So if this is an open circuit, then we can further simplify this. This should be 2 ohms rather than 6 ohms because we've replaced it with the equivalent resistance. So we can further simplify this as a 2 ohms with this source, the switch, and this 2 ohms. So this is a 10 volt. Right now, we need to find out the current through this. So we can apply KVL here, and it is pretty simple because this 2 ohms and this 2 ohms, they are in series. So I have actually precisely removed this branch because it's open circuited. No current is going to enter this branch at all. So the entire circuit current, say I'll call it as I, is going to be 10 by 4 amps. So 10 by 4 is going to enter this particular branch and then it's going to split up. In either case, we don't need to compute the current flowing through the 6 ohms because the voltage drop across this entire parallel combination is going to be the same. So, since we know the current entering this parallel combination is 10 by 4, we can just find out the voltage drop across it as V is equal to 2 into 10 by 4. Why 2? Because the parallel combination of 6 and 3 is nothing but 2. So precisely we have computed the current entering here as 10 by 4, and therefore the voltage drop across these two terminals is 5 volts, which is nothing but the drop across these two terminals, which is again the drop across 6 ohms resistor. So the answer to this question is 5 volts. Let's move on to the next problem. So this is the second problem. Here they say that the switch S was in the closed position for a very long time. So this indicates that it was in a steady state, right? This switch S was closed. Now look at the position of this switch. So we can redraw that condition when the switch was closed. So it's simply going to be this 10 volts, and there's going to be a short circuit over here because the switch is closed, and then this 4 ohms, this 30 volts, then we'll have this 1 ohm, zero point 0.5 Henry, 1 ohms, the short circuit, the 4 ohms, the 30 volts, and the 10 volts. So they say that this switch was closed for a very long time. So it means that if there is a short circuit present over here, there's no current that is going to flow into this branch as such. So we might as well not consider this branch. So effectively, the circuit was actually looking like this. So this is the initial condition. And since this switch was closed for a very long time, which means the circuit was in the steady state, so the inductor would actually be acting like a short circuit. So let's remove the inductor 2 and replace it with a short circuit. So on doing that, we can actually compute the short circuit current too. So now this circuit essentially boils down to this voltage source and this resistance of 1 ohms. Therefore, the current through this short circuit branch, which I would call as I naught, the steady state current, will be equal to 10 amps because 10 divided by 1 is going to be 10. So we have found out that I naught is going to be equal to 10 amps. Now the question says if the switch is going to open at time t is equal to 0, we need to compute IL of t for t greater than equal to 0. So now, since when the switch opens, the circuit is going to look different, right? So this is t less than 0, for this is t is equal to 0. How is it going to look? So I'm going to have this. There will be this 4 ohms, the 30 volts, 1 ohm, and there is going to be an inductor of zero point 0.5 Henry. So this is zero point 0.5, this is 1 ohm, 30 volts, 4 ohms, and 10 volts. So now the current IL of t, so this is going to be like exponentially rising. Why? Because there's an extra source that has come into the picture. So there's going to be more current flow into this inductor. So there is going to be a homogeneous solution to this current and a forced response. So I'll call it IP of t, particular solution to this. Now, what is the particular solution? So that is going to be computed. We can do that using KVL by applying KVL to this. So we are going to consider that this is how the circuit is going to be uh, for t tends to infinity. So which means what? It means that this inductor will act like a short circuit at that time. And now if we apply KVL to this, we'll be able to compute the current over here, and that will be my IP of t, the forced response. So on applying KVL, I get, let's mark, uh, assuming that this is the direction, plus minus, this is minus plus, plus minus. So consider that this is the direction of my current, okay, and the voltage drop direction. So the drops are like this, from positive to negative. Now we can write KVL as minus 10 because it's opposing our assumed direction, plus 4, let me call it as IP, and minus 30 plus IP is equal to 0. So I have 5 IP is equal to 40. Therefore, the particular solution IP of t in this case therefore becomes 8 amps. So the forced response or IP of t here is 8 amps. What is IH of t? So IH of t is given as A e power minus t by tau. So this is an RL circuit. So tau will be equal to L by R. And what is A going to be equal to? We need to compute that. So before that, let's find out L by R. So L over here is 0.5 Henry. And what is R? So if we look at this circuit, effectively, R is nothing but 4 plus 1, which is 5. So the resistance in this circuit is 5 ohms. So 5. So that is 0.1. So we can say this is A e power minus t by 0.1, or A e power minus t into 10. So therefore IH of t is found as A e power minus 10t. Now we need to compute A. So we know that at t is equal to 0, I was actually 10 amps, because that's what we've computed it as. During the steady state, when it was like a short circuit, it was acting as a short circuit and 10 amps current was flowing through it. That was when the switch was closed, right? After that, the switch got opened and it reached a new steady state. So we are finding out the response, the natural response of this inductor for the second case when the switch got opened. So we can replace this over here. So IL of t is equal to 10 amps, which is nothing but A e power minus 10t plus 8, where this is the homogeneous response or natural response, and this one is the forced response. So this 10 is the current when time t is equal to 0. So I can put this t as 0. So what I obtain here is 10 is A e power minus 0 plus 8. E power 0 is nothing but 1. Therefore, A is found out to be 2. So essentially, IL of t is equal to IH of t plus IP of t, where IH of t is nothing but 2 e power minus 10t plus IP of t is 8. So option C is the correct answer for this question. So this is how we analyze RC and RL circuits for steady state. And we need to remember that during steady state, the capacitor acts like an open circuit and the inductor acts like a short circuit. That's all with today's video. In the upcoming videos, we'll see more such problems and take up more complex RC, RL, and even RLC circuits and analyze them. Please do subscribe to this channel. Thank you.